Hello and welcome. It is my pleasure to introduce Professor Kiruluta of Harvard University. He is a biomedical physicist and holds joint appointments at the Harvard Medical School and in the physics department. He is also the director of the Clinical Magnetic Resonance Physics department in the Department of Radiology at the Massachusetts General Hospital. And his team is responsible for all the MRI scanners in the Mass General system. And he's going to tell us about how the brain is wired. So without further ado, Professor Kiruluta.
Thank you so much for that generous introduction. Can you all hear me at back? OK. I'm going to talk to you about a very exciting area of imaging that looks at not just at structural information, but looks at functional information. And the future of imaging is not just looking at how structure is laid out, which you can get through dissection, but actually looking at disease processes at a cellular level. So the images I have here on the left and the right are images of how the brain is connected through fiber tracking, which I'm going to talk about in this lecture. So once upon a time, this is how we looked at images. This is how we found out what's wrong with somebody, through access points that allow us to see whether or not there is a disease somewhere. The alternative to this is, of course, to dissect and try to find out what the issue was. But we've moved on, and we have a number of ways of actually looking at images that does not require dissection, ranging from ultrasound to X-ray to CT and finally to MRI. So ultrasound is typically used in looking at fetuses, but the resolution is very poor. It's cheap, that's why it's very widely available, and it can be done off-site. X-ray is the next revision of looking at imaging, but the problem with X-ray is you don't get very much soft tissue contrast. You typically look at solid things like bone. Then we go to computerized tomography, or CT. That's based on X-ray, except that in this case, the X-ray is applied all around the subject to generate these projections that allow you to be able to resolve small differences in tissue attenuation of the X-ray. And that gives you some soft tissue contrast, and it's fast. But you don't get very much soft tissue contrast regardless. So the best modality for looking at soft tissue contrast is magnetic resonance imaging. And with magnetic resonance imaging, we've been able to get amazing images. These are dissections of the brain. This is called a sagittal slice. It's basically a slice like this that allows you to see things like this is the brain over here, your synovial fluid is over here, the nose, and so on, with much higher level of clarity. Unfortunately, the resolution in this case is about 0.1 of a millimeter is the best we can do with current technologies. So what we're looking at is basically what you'd see if you dissected someone. And it doesn't tell you much about the disease processes other than grayscaling these levels. So if you had a tumor, the tumor would show up as a bright region. Okay? And if the tumor is just, if you're on the onset of a tumor, you probably won't see anything. We also have MRI images that allow you to image somebody from head to toe, like in this case. And also, we are able to image just the vasculature. So this shows you how the brain is fed by the multiple capillary tree that the blood is coming through from the heart. So this shows you how all the little vessels are interconnected within the human skull. And this type of imaging is called magnetic resonance angiography, and it's based on the phase information that you get from blood as it moves through the brain. So that's the level of sophistication we've come to. More recently, we've been looking at even higher level of resolution. So what I'm showing you here are corticospinal tracts. These are tracts that actually show you the interconnection of the wiring of the brain at a level of a micron level resolution. So much, much smaller than the 0.1 millimeters, the 0.1 centimeters that I talked about. And in this talk, I'll talk about how we generate these kinds of images. How do we go from a device that was designed to see things at close to a millimeter to something that is at a micron level resolution? In this picture, what I show is this is a brain that was dissected. I apologize, the picture is not very clear, but I don't know what happened. But so this is a dissection of a brain where somebody has injected dye to show these corticospinal tracts through a dye method. And this is what we get if we use an MRI type system approach that I'm going to talk about. And it shows you that there's good correlation between something that was done through dissection and something that is done in a way that's non-invasive, basically putting a human being in the brain, in the scanner, and being able to generate these kinds of images that show how the whole brain is wired. And this is really the future of imaging. So the future of imaging that I'm going to talk about here is not just imaging structural information, but looking at how cells, how the biophysical processes in the body are interacting with each other at the cellular level. In other words, we'll be able to see diseases at a cellular level. It's typically called functional imaging or molecular imaging, and this is what I'm going to be talking about here. So these kinds of images are generated from a process called diffusion. Okay? MRI fundamentally images water. The body is 80% water. So any area of the anatomy that has a lot of water will show up as a bright signal in this case. Any area that doesn't have a lot of water will show up as dark. For example, bone doesn't have much water, so MRI typically shows no signal for bone. Now, this water is concentrated. Sometimes the water is more concentrated in certain regions than in other regions, so they will have different contrast. That's how we tell, say, for example, gray matter from white matter, because the water concentration is different. Okay? So this is only looking at water that is trapped within the tissue that we're trying to image. The next revision we're going to do that will allow us to get much higher resolution is to look at water that is just randomly wiggling within the tissue, basically water that's diffusing. Before we do that, we want to talk about what diffusion is. So diffusion is just a random movement of molecules within themselves. So for example, if I have a jar of water over here and I put some ink in that jar, that ink will spread through the volume of water. Okay? And that process is driven by diffusion as the molecules wander around within that region. So this region over here that didn't have any of the ink particles will eventually equilibrate as these ink particles migrate all the way through these pores and go in this region as well. So what we're going to talk about is over a period of time, you have an equalization of those two chambers as those things wiggle around. So you can think of every tissue in your body also has these water molecules that are wiggling around and moving from place to place. And we're going to find a way in which we can actually measure them and use them to tell us something about the underlying structure that is either allowing the water molecules to move around or restricting that water molecules to move around. So if I have a water molecule, say this water molecule, and it's wiggling around, and there's no restriction in the extent in 3 dimensions how far it will go, over a period of time, it's going to map out a sphere. It's going to wiggle around like this in 3 dimensions, and will eventually look something like this. And that follows a Gaussian type distribution because diffusion is free, the particle is not restricted in X, Y, or Z. It can go in any direction. So if that's the case, what we end up with is the particle is free to go in this direction, in that direction, as well as in and out of the board. So we end up with a spherical type description of where the particle is going to be in a given amount of time. But we know that biological structure cannot be like this. You cannot expect a water molecule trapped into some tissue to wander around freely with no boundaries. We know that there are boundaries in biological systems. So if there's a boundary, then you're going to find that the particle is free to wander around in this direction, but as it wanders over in that direction, there is a restriction as to how far it can go. So we'll end up with a structure that looks like this when diffusion is completely unrestricted, or a structure that's cigar-type shape if diffusion is restricted. Okay? So in reality, what we're going to end up with when we measure diffusion is we're going to end up with these types of cigar-shaped structures because of the boundaries of the tissue to the water that's moving back and forth within them. So, and here's where it gets tricky, but I'll just summarize by saying that the way we measure diffusion is we run a sequence, an MRI pulse sequence, that has 2 gradients. And the gradients are opposite to each other. In other words, they cancel out each other. So as the water molecule wiggles through these two gradients, it will see this gradient over here, and then it will wander around and then see another gradient over here, which cancels whatever this one did. So there are three separate scenarios. If the water molecule is stationary, then it will see this gradient over here, okay? And after a period of time, big delta, it will see another big gradient, but it's opposite to the other one, and it will cancel out. So the net effect of that is that for a stationary type water, there will be no change in the signal because it saw this gradient and it saw that gradient. If the molecule is moving, for example, in blood, it will see a fraction of this gradient and a fraction of that gradient, and they will not cancel out entirely. And you end up with a phase loss that sort of reduces the signal, but not by much. However, if you have a water that's diffusing within a given volume, and that water is diffusing over the period of time that we've applied this gradient and that gradient, it will only see a fraction of this gradient and will only see a fraction of that gradient. And the total sum of that does not equal to 0. Consequently, the signal is much smaller in that case. So you can think of gradients as applying a phase. So they put a phase on your water that's moving, and then you apply another gradient that's opposite that, which applies a negative phase, which basically cancels out the previous phase. But you can only cancel out the phase entirely if you saw both gradients in their entirety. You saw them in full application. In this case, you don't see this full gradient and that full gradient, so the diffusion signal goes down. So you might ask yourself, why is this a good thing? Our signal is going down, so how are we going to exploit this? So you take two images. One image you take is a conventional image, and the other image you take is the one with those two gradients applied. Okay? The ratio of these two images will give you a sense of what area of these images are experiencing diffusion. Okay? So this is the sequence over here, and this is basically the equation that you use to determine what image, so this is the signal with no attenuation, with none of the gradients, and this is the signal with the gradients applied. So this is reduced by this fraction amount due to the diffusion that is going through your object. So if that's the case then, and we know that biological tissue is basically fibrous, consists of different fibers, we're going to ask yourself the question is, if I look at a single pixel in that image, that single pixel in that image will consist of a water that's moving either freely in all directions or moving along a given direction because it's restricted in some other dimension. If that's the case, if you have a bunch of fibers like this, then you have diffusion in all different directions, you end up with something that looks spherical. If you have fibers that are all aligned in a given direction like this, then of course you're going to have diffusion more free in this direction and restricted in that direction. So you're going to get that cigar shape back again. If you have crossing fibers like this, you're going to get diffusion more free in this direction and diffusion more free in that direction. You're going to end up with that structure. So in order for you to be able to resolve where the water molecule is moving, you need to apply those gradients I talked about in 6 different directions. Right? You need to know whether diffusion is going, say, left to right, up and down, or in and out. Okay? And in order for you to do that, you end up with this matrix over here. So you can think of, for each single image, and I'll touch on this, for each single image that we're getting before, now we apply gradients in 6 different directions to look at how the diffusion changes in those 6 different directions. If we do that, we end up with, if we're looking at diffusion in the x direction, this is what the image looks like. If we're looking at the diffusion in the xy direction, this is what the image looks like. And finally, if we're looking in the z direction, this is what the diffusion looks like. So you end up with this set of images corresponding to this resolution of those different directions. Okay? So take a pixel. If you pick this pixel over here, that pixel over here is repeated 1, 2, 3, 4, 5, 6, 7, 8, 9 times. So that single pixel has 9 components to it. But this is the same pixel. Okay? So what we've done is we've applied these gradients in these different directions to resolve the direction of diffusion. But we end up with each pixel has 9 copies of it for those different directions. So the question is, how do we then represent this information? We have a lot of images. How do we then present this information in a meaningful way? Okay? So if you want, for example, to measure the diffusion in the xy direction, you apply gradients in x and y at the same time. Okay, so this picture shows you what happens right now, which is we have a 3-dimensional object, for example. We take a slice, an axial slice. There's a slice through the head like this, going like that. Typically, what you have is each pixel here tells you the position in space of that slice, of that pixel in that slice. What we're going to try to do now is we're going to look at, in a given pixel, where does the water wiggle to? Does it move in the x direction? Does it move in the y direction? Does it move in the z direction? Or doesn't it move at all? And that is a different type of image called a 3-dimensional displacement space image. Okay? So these 9 slices I show are a way of determining the direction for each of the pixels in our image of whether or not the pixel has water that's moving in a given direction. Okay? So for each one of these pixels, we have 9 directions, 9 pixels. Similarly, we'll have a pixel here. We'll have this is what it's going to look like in displacement space. So we have 9 pixels here, and we're going to show how do we then represent that image. Okay? So given the fact that for each pixel, we have 9 different pixels representing the direction of where the spins are moving or the waters are moving, how do we represent this information in a meaningful way? And this is the concept of tensor imaging. So some of you may recognize this matrix as a matrix that needs to be diagonalized to get the eigenvalues. But basically, when you do the math, it turns out that that 9-element matrix that we had, we do the math, we get the eigenvalues, and we get these pictures. These are the 3 possible pictures. So for each one of the pixels that had 9 different representations of where the diffusion is going, we can have that the diffusion is free to go in any direction, in which case we have a sphere, or the diffusion is only free to go more in one direction than another direction, in which case we end up with a cigar shape, or that the diffusion is free to go in both these directions and more restricted in the direction that's going up or down like this. So, in other words, for each one of the pixels that we have, and we've resolved the diffusion in 3 different directions and got 9 different pixels for each pixel, we can do the math and determine which of these 3 shapes that pixel belongs to. And then we present another image where each pixel is represented by one of these shapes over here to represent where the diffusion is going. So that's one way in which we can represent the information. Any questions so far? OK, so the other concept that you could use to represent the information is this concept called fractional anisotropy. And what basically it says is, of these 3 shapes, geometrically, how can I describe those shapes? So this sphere here shows that diffusion is free to go in any direction. So the fractional anisotropy in this case is 0. Right? There is no preference for any direction. So fractional anisotropy is a measure of the preference of diffusion. What is the most preferred direction? So the fractional anisotropy here is in this direction. It prefers to go more in this direction. So the more cigar-shaped a pixel is, the higher the fractional anisotropy. It means it's more likely to go in one direction than the other. Okay? So of all these 3 structures, this one has the highest fractional anisotropy. So you could use that to say, OK, I'm going to represent my object in terms of fractional anisotropy. And this is what this object here shows. So you take that pixel that had 9 representations of the different diffusion directions, and each one of those pixels, you represent them with this fractional anisotropy where you say, OK, when I measured this pixel, I ended up with a sphere, meaning that diffusion is free to go in any direction, in which case that pixel will be black. And then you go to another pixel and you say, okay, when I measure diffusion in that direction, I found that the diffusion was preferred in one direction than the other. It's more cigar shape, in which case it has a very high anisotropy. I'm going to give that a white color, and so on. In this case, it's reversed. When the diffusion is free in all directions, I give it the color white. And when diffusion is more preferred in a given direction, fractional anisotropy is high, I give it a color black. Okay? So that's what you're seeing. That's one way of representing it. The trouble with doing it this way is the direction of the diffusion is lost if we do this. Okay, so typically, this is an easy way of doing it, but we lose the direction information. The other way of doing it is do it this way, is to look at color coding the directions of diffusion. Okay? So if we color code where going up and down is blue, when diffusion is up and down, we're going to say it's blue. And when it's going in this direction, we're going to say it's green. And when it's going in the other direction, we're going to say it's red. Then for each pixel, you determine the direction of diffusion, and you represent it, you replace that pixel with a color. Okay? So if you look at this image, it shows that you have green areas like this. That means that diffusion is more free to go in this direction. So it's going in and out of the board like this. Similarly, in this case, where you have blue, it means that diffusion is more likely to go in this direction along those pixels. So you take each and every pixel and represent it by a color corresponding to the direction of preferred diffusion. And these are the images you end up with. The simplest way is the one I talked about before, which is we're just going to represent each pixel with the shape corresponding to the diffusion that we've generated. There are two basic shapes. Well, actually, there are three basic shapes. We have a sphere, we have an ellipse or a cigar shape, and we have something that looks like a pill. And we're just going to represent each and every pixel by the corresponding shape that we want. You can, of course, instead of using a sphere, you could use a box like this, meaning that diffusion is more free in this direction than along this dimension. Okay? If you do that, you end up with, for example, if we just blow up this area over here, you end up with each one of these pixels being represented by this box. And this box tells you that diffusion is more free in that direction than in this direction. So each one of the pixels is being represented by these individual blocks that we've determined from the calculation, with the colors representing, as in this case, so blue is coming in and out, anterior, posterior, so that means that diffusion is more free in this direction, and green meaning it goes in that direction, like this. As you can see, I've only blown up this section just to represent each one of these pixels by where the diffusion is going. So it gets very complicated in a hurry. Okay? So these are the three different ways you can represent it. So you can represent it by boxes, you can represent them by little pills, or you can represent them by these little boxes that look like super, well, they're almost like super boxes, but with no edges on them. So you can represent like this. But the point is, it gets very complicated in a hurry, because if you want to represent now the three-dimensional object, you have to represent each pixel by one of those little figures. And it gets very complicated to look at. Okay? It's not the most effective way to present this information. So tractography tried to solve this problem. So if we go back here and look at this individual pixel, you can see that each one of these pixels is pointing in a given direction. So it tells us that there is diffusion freer going in that direction. So we just need to join these boxes that are next to each other with a line showing where the diffusion is going, and then stop when we reach the end of that line. And that's the concept of tractography that I want to talk about. So what we basically do is we go from each one of those individual pixels and we look at what direction is the diffusion more free. Then we look at the next pixel. If the direction that is free is close to this direction, we just join those two. And we keep going like this from pixel to pixel. And that's how we generate the tracks. There are, of course, certain rules we need to follow in order to do this. So some of the rules we need to follow is we have to go from pixel to pixel. Have to go from step to step. In this case, we have 1 millimeter resolutions. We're going to go from one pixel to the next pixel. The next thing we need to care about is this thing called fractional anisotropy, which is basically the measure of how much of a shape is a cigar as opposed to a sphere. So if it's more cigar shape, the fractional anisotropy is higher, and if it's a spherical shape, the fractional anisotropy is lower, which means the diffusion is free to go in any direction. So you need to track as you go from pixel to pixel joining them, is my fractional anisotropy still high enough to justify connecting to the next pixel? And then the other thing you have to worry about is in nature, we don't expect these tracks as we map them out to all of a sudden make these sharp turns. So we don't expect a track to go like this and all of a sudden it makes a 90-degree turn. So we have to worry about the angle that we are generating. If the angle is too steep, it's not realistic, so we stop. So these are some of the heuristic rules we have to follow based on some observation of natural phenomena. So the idea then is tracks are computed from one pixel, either going forward or going back from initial C's that we determine, and then we use multiple C's to go to the next step. So we read in that matrix that I showed you, which represents each pixel as 9 different representations of diffusion directions. We do this mathematical technique of generating the eigenvalues and eigenvectors, which basically tells us what shape it is. Is it a cigar shape or is it a spherical shape? We check to see how cigar-shaped it is. If it's not cigar-shaped enough, the fractional anisotropy is too low. If it is cigar-shaped enough, then we can move on in that the diffusion is going in that direction. If the fractional anisotropy is high enough, we go on to the angle criteria, make sure that the angle that we're going to go through is no more than 45 degrees. If that's the case, then we step onto that pixel and then do the same thing for that pixel by generating the matrix, by diagonalizing the matrix corresponding to that pixel in order to step onto the next one. Okay? And after we finish all this process, we output the tracks. And this is a method that was proposed by 2 researchers at Hopkins and at NIH. So if we do that, we end up with images that look like this. So what I'm showing here is an axial slice through the brain. So the brain is being sliced like this. Okay? And we do this diffusion experiment, and we join the tracks. And when you do that, you find that the slices, as you walk from the lower part of the brain going up to the top of your head, those slices are joined by these corticospinal tracks, basically the wiring of how each slice of the brain is connected to the next slice of the brain. Okay? What we effectively are measuring is that the water is more free to move in this direction than in that direction. And from that, we're inferring the structural information about how the brain is interconnected in that way. So these are tracks. Similarly, we can look at this in the tracks that are going from my eyeball, for example, back to the back of my head. Again, these are tracks that are going like this. Okay? And these are sub-micron level resolution tracks, right? And we're generating these from a system that was designed to give you no more than 0.1 millimeter resolution. So it's a mathematical trick that allows us to go deeper in our level resolution. Okay, so this is fiber tracking in a normal volunteer. So you can see the eye would be here. These are the tracks that take the signals to the brain for the visual cortex over here. And of course, you can see these tracks over here, which shows you some of the limitations of the method, that somehow it thought there were tracks going over here, but there were no tracks going over there. So that's just an artifact in the algorithm. And these are tracks, again, that interconnect through the brain going this way like that. So how is this useful for, say, future clinical practice or current clinical practice? We did some fiber tracking on somebody with a tumor. So a tumor is sitting over here. It's a bright region in an MRI. And the reason why the tumor is bright is because you have cells piled onto each other. So a tumor is a runaway process where cells divide and keep dividing, and then they create this big lump. Okay? So if you have a lot of cells lumped together, there's a lot more water there than adjacent areas. So you end up with a bright signal over here. If you do fiber tracking, you find that where the tumor is located, the tracks are being cut away. So they are pushed away. So if this is in fact a brain tumor, it means that there's a deficit over here in terms of where the tracks are located. And that has implications for a surgeon if they have to go in and take out that tumor. And we'll talk about that shortly. The other application of this technique is, for example, there are people who do studies of infants from birth all the way up to their teenage years, and they're looking at how these tracks change, which basically the interconnection of the brain, how it changes over a period of time. So you can imagine that if indeed these are tracks that are showing, which they are, brain interconnectivity, that means that you can monitor your child to see whether or not they're developing on an adequate path based on how much of this density increases over time. And if the density is not increasing over time, you know that something is wrong in the development process, and some intervention could be done. But more recently is we had studies, for example, where somebody comes in with a huge tumor, a glioblastoma right here, massive tumor. Okay? This tumor here has to be operated on by removing that tumor. In the past, what the surgeons did, they would just cut out that tumor. Okay? They would cut out that tumor and hopefully take out all the tumor so that there's nothing there left, and you have basically take the tumor out. But the problem with that, in the past, the surgeons, when they cut out this tumor, they noticed that they would cut these little tracks as they were cutting out the tumor. And this person would wake up with a significant deficit. And the reason for that is this person was lucky enough to go through this tractography idea. So these are corticospinal tracts that are connecting the whole brain to the spine, which is going to be down here. Notice that where the tumor is located, the tumor has pushed the tracks to one side, has exerted a lot of pressure to one side, so that the tracks are moved over to one side. Now, if a surgeon came in blindly and removed this tumor without paying attention to where these tracks are located, this person will wake up with a significant deficit in terms of mental function and other motor activities. So this person benefited from this experiment, from this corticospinal tracking. And so this is the image that you see pre-op. This is the image you see after the tumor was removed, and you can see that the tracks have now sprung back into position. But the most important point here was the surgery was done under the guidance of where these tracks were located. So the collateral damage of cutting a lot of tracks was minimized by the fact that the surgeon had this information in front of them. Okay? And in fact, at MGH, Massachusetts General Hospital, they just installed an interventional suite where the surgery will be carried out and a magnet will actually come to the patient. So the magnet is sitting on rails, it will come to the patient, they will do the imaging, see whether or not the tumor is being removed, see whether or not the corticospinal tracts are still intact, and then they'll go back, they'll continue the surgery, and then they'll come back. So interventional guided procedures are aided significantly by this kind of high resolution information. Okay, any questions so far? Okay. Can say it can be one of two things, either I'm completely lost everybody or...
Is there a hole that remains, or is it subsequent?
There's a hole that remains. So the hole will remain here. And this person will come back 10 years and you do an MRI image and there'll still be a hole right there. Okay? Yeah. But surprisingly, this person has all their all their previous functional activities back, even though there's a big hole in their brain. And that's the power of the plasticity of the brain.
Does the hole create an opportunity for some of the rest of the matter to, shift to fill that space that's opened up?
That's more of a biological question than I'm equipped to answer.
Okay,
but
okay.
I suspect that so I've seen these images where people show up and they still have a hole there. So it's not filled with fluid or anything like that. But whether or not this area here expands slightly, I don't know.
And the same amount of the tumor is removed even with this process?
Yeah, that's actually a very, very good point. So in the past, what the surgeon would do is they will know that so you go in and you have MRI done on you, they know there's a tumor, they start planning the surgery, and the surgery is planned for weeks, many, many weeks after you've gone in for the MRI. And typically the biggest complaint of surgeons is this tumor shifts, it changes, and they don't have access to that information at all by the time they do the surgery. And that's one of the reasons why we want to do interventional guided procedures where they can actually see in real time what the state of the tumor is. So, but in the past, what they would do is they would take out a lot of areas outside of that tumor just to make sure that as much of it as possible is gone. But that is still based on old information, that the tumor's boundaries were defined like this, which is never the case because the patient goes home, they worry, they lose weight, they gain weight or whatever. So the tumor shifts, and also the tumor as an animal is growing during that time.
An extra margin, you know, off of the tumor would be removed as well?
An extra margin will be an extra margin will be removed just to make sure that the tumor is entirely gone.
Okay, thank you.
Okay, and during the removal of that extra margin, this is when potentially these cuts are made. And if you cut too many of those tracks, then the deficit is much, much larger, and it's unrecoverable.
Sorry, if the tracks are actually cut or damaged, do they grow back, or do they regenerate themselves?
No, they don't. No, they don't. In fact, this is one of the reasons why fiber tracking is important. It's because they don't grow back. You have a lot of tracks. There's a lot of redundancy, but there's a limit to how much abuse you can give them.
And so will that then affect the track that follows on from that? Obviously, if the track is cut off at a certain point, will then the rest of it die, or how does that?
Basically, you can think of a track as your wiring. So the signal will not go to its destination along that track. But like I said, there's a lot of redundancy. That single track doesn't do everything. There's a lot of redundancies. For example, all these tracks do the same thing as these tracks over here, right?
You cannot change the way of the track?
You cannot what?
Can you move the track?
So these are micron level resolution. So they are very, very, very small tracks, right? So the surgeons doesn't see them. In fact, only through clever tricks in imaging that we are starting to see these tracks, although we've known that they exist. So you can't really change the direction of the tracks, no. Yeah.
If that's the case about they're not visible except through this imaging, how in the surgery, is the surgeon able to tell whether he is about to cut into them or not? If only he has the picture together.
Oh, so basically what happens is this is the picture that the surgeon sees. This is the picture the radiologist sees. And the radiologist knows that there's a tumor over here and tells the surgeon that this person is a tumor. So then they start planning surgery. So they put a grid over this to determine, in relations to your head, where exactly that tumor is. And they come in and they extract out that tumor. So there's a lot of processing, mapping that happens. This is not just a single slice, so it will be for the whole head. So there's a whole three-dimensional mapping that happens for the surgeon to know exactly where the tumor is. And this is part of the biggest problem, which is the fact is it takes a long time to do the physical mapping of where this tumor is and then do the surgery. And by then the tumor is sort of shifted.
Yeah, can you say a little more about what these tracks are comprised of? Are these axons?
Yes, there will be axon bundles.
Okay.
Yeah. So yeah, I should use the proper terminology. They are axons.
What are an axon? What's an axon?
An axon is the electrical wiring that takes the signals down to the areas where the signal is required. So these are the actual wires, the wiring. The electrical activity is conducted by these tracks. Biologists call them axons. Yeah.
So if some of the portions are removed from the brain,
Yes.
that portion will have some function, right? So for example,
Yes.
associate.
Yes.
So how would that, for example, if you remove that particular area,
Yeah.
it may impact on some functionality of the person, right? Because these axons basically come from those areas as
Yeah.
well from the where tumor
Yeah.
is removed, right?
Yeah.
So still the person may wake up with some deficit of activity.
Yeah.
Yeah?
So if the brain was wired like that, we'll all be in trouble. Because accidents and diseases are quite common, and one part of the brain gets affected and so on. But the brain, as to use a common terminology, is very plastic. So those activities are offshored off somewhere else in your brain. And new connections are made. And in fact, this is one of the beauties of doing this technique is you can actually follow, if you could do the whole brain mapping of these tracks, new connections will be made to offset that deficit. Of course, there's a limit to how much of the brain you can take out before the function is completely eliminated. Yeah. Yeah.
Is the treatment plan to include both surgery and maybe gamma knife or some other kind of radiation treatment afterwards to go maybe more precisely to remove more of the
Yeah. There are people who do those kinds of things where so typically what you're talking about is somebody who is conservative enough will remove the tumor, but not remove it entirely around the boundaries. Okay, they will leave the boundaries to be removed by radiation therapy. Okay, so that's typically what is done.
Why is radiation less dangerous than the knife?
Oh, then the radiation will not cut the tracks, right? It will be targeted towards the tumor, which will uptake whatever whatever material you've targeted it with. Yeah. So the peripheral of the tumor could be treated like that. Any other question? Yeah.
These tracks are like highlighting information of brain activity going through the brain, I guess.
Yeah. So the gray matter, somebody asked, the gray matter contains the actual. So the gray matter contains the actual processing itself, right, of the signals. And the white matter contains these tracks, which is the axons, which carry the information somewhere else and onto the spinal cord, and of course to various nerve endings. Yep.
So just to follow up on that, so and you're measuring water flow.
Yes.
But the axons are carrying electrical information.
Yes.
So where does the water come into it? Is this the neurotransmission?
That's a very good question. I should have mentioned at the very front that the body is 80%, over 80% of us is water, okay? And if over 80% of us is water, so the tracks themselves, right, whether you look at the material that makes up the track or whatever fluid is in there has to be some water, so H2O in some form, either bound or unbound. So MRI measures hydrogen, right? And hydrogen is attached to water. So basically, MRI is just a mapping of your water distribution, which is what we are mostly. So we're not actually looking at electrical activity as per se, but we're looking at water distribution, which is what we are made of anyway.
And that water flow is correlated with the flow of electrical impulses as well?
That's a big step for us to jump. We have not made that step, but we know that. So basically what we're measuring is coherences. We're measuring we're measuring this boundary which defines the axon, okay? And the water that's bound in there, that's in there, is restricted from moving in one direction, but is freer to move in another direction. From that, we're inverse imaging something we're calling an axon. But we have not connected to electrical activity. And people who are trying to do that, the only way MRI gives us some window of electrical activity through something called functional MRI, fMRI. Okay, I don't know whether most people are familiar with it, but briefly, if a part of the brain lights up, basically a part of the brain has electrical activity. That requires energy. And energy comes from oxygen flow through blood. Now, blood carries oxygen through hemoglobin. And hemoglobin itself is iron. It's got an ion component. So when oxygen attaches to hemoglobin, it shelters away the ion away. Okay? When oxygen is released from the hemoglobin, basically deoxygenated blood, the hemoglobin ion is exposed. Now, ion is important because MRI works on magnets, and ion is magnetic, so it changes the magnetic signal. And that little change tells us, this part of the brain light up. Again, another trick that gives us a window into electrical activity. So there are people who are trying to tie the endings of these axons to fMRI. And then say, so the signal lit up here is going to this area. Yeah.
There are some people that have more water in the brain than other people. Does the plasticity of the brain apply that there's no loss?
So when you talk about water, you talk about free water.
Yeah, the thing in the middle, you know.
The thing in the middle.
Is that waterhead or something?
Yeah.
And it gets flattened. Does the plasticity apply to that?
Yeah, it will apply to that, but that's outside the brain, right? It's not in the brain itself. So within the brain itself, I will not see that water content.
Yeah, so it's outside, it's in the middle. It pushes the brain towards the skull and it gets flattened.
What gets flattened?
The gray matter gets flattened because there's overpressure in the brain.
Yeah.
With the water that, like some children are
Yeah.
born with big heads.
Yeah, yeah.
Does the plasticity apply to that the brain will still work?
Oh, you mean the plasticity to the brain to pick up new function? I don't know. Okay. Again, that's more biological.
But they normally die, these babies.
Yeah, I don't know the answer to that question.
And one last question is, in analog or digital, the signaling, the signaling that you're referring to?
Oh, the electrical activity in the brain?
Yeah.
No, it's not binary. No, it's not binary. So a neuron to fire on, it requires a threshold. So when the threshold is reached, the neuron fires. But it's not just one neuron. There's a multiple number of neurons that fire. And that signal is somehow is processed to send down a signal. If it's not enough, nothing is sent down. So it's much more complicated than our simple binary system. It's got millions of years to...
Okay, so we have research.
Yeah, we'll catch up. But then we'll never catch up because it's whatever time will take for us to get there, the brain will also be evolving, yeah. Hopefully. Okay, so it's not all paradise though. It's not all paradise that this method works. Here's an example. We're measuring coherences. So suppose we have a band of fibers together like this. We'll come up with, so we're not really looking at individual neurons, right? The individual neuron is like less than a micron. What we're looking at is a band of neurons, okay? And that band of neurons, in this case, happen to be pointing in that direction. Then we get them to be represented by a cigar shape that looks like that, which is consistent that diffusion is more free in this direction than it is in that direction. But supposing, instead of having a simple band of neurons like this, we had some of the neurons were like this, and then some of the neurons, again, someone's going to say, oh, that's too sharp an angle, but for demonstrative purposes, I'm showing that some of the neurons are going like this, okay? If we use our method, it would show that diffusion it's going to come up with a shape that looks like this. Diffusion is free in this direction, and it's got some funny shape that looks like this. So do we have a sphere here, meaning that diffusion is free in that direction, in that area here? So that's unresolved. So if we have fibers that are going in different directions, we run into problems, okay? Another problem we run into is this. Suppose we have crisscrossing fibers like this. We know that diffusion is free in this direction. That's why we have a cigar shape that looks like this. Diffusion is free in that direction. But what happens in the case where you have overlap? Where we have overlap, diffusion is free in that direction, and diffusion is free in that direction. We end up with a shape that looks sort of like that, okay? Similarly, in this direction. So if we're to do a tractography says connect this to this because it looks like diffusion is free in that direction. But what do you do when you get here, where it looks more like diffusion is free? Should you go like this, or should you go like that? So this situation is indeterminate. So if you have crossing fibers, it becomes indeterminate to do. So how to resolve those difficulties? Well, those difficulties are resolved by doing diffusion in a lot more directions. So I say you need a minimum of 6 directions to resolve this problem. But instead of doing that, people typically do 42 or 62 directions, meaning that we do a repetition of other directions. And that gives us more resolution in terms of where the diffusion is going. Okay? So the trouble with this, of course, is it's going to take more time. So every direction you do is going to take more time. You're going to get more data, and that data needs to be processed. There's an underlying message here, too. A lot of this stuff was not possible before we had huge processing power, right? Because every single pixel here is being represented by this massive matrix that we need to play around with to determine what shape that pixel is going to be. And that requires processing power. So by taking a lot of directions, we can play tricks like this where a single pixel is eventually broken down into something that looks like this. In this case, I can resolve crossing fibers in this method called diffusion spectrum imaging by subsampling my pixel, by looking for one direction in which that diffusion is going. And I do that through this series of steps that I show over here. Okay? If we do that, then we end up with structure that look like this. This is much higher resolution than the simple method I just introduced. This is some of the images I showed you before that show you the whole brain interconnection based on this method. And of course, you see all the fiber tracks are eventually running over to the spinal cord. Okay, so another way we're looking at this, so I'm getting to the research areas. The stuff I talked about before is now being used in major clinical areas for helping people on a day-to-day basis in terms of tumors and so on. But the stuff that I'm talking about now is, I'm summarizing now, is based on research. What other areas can we look at? So when a water is diffusing, what we've looked at is how the water changes position over a period of time. Okay? So if diffusion is slow, it's going to change position at a slower rate. If diffusion is fast, it's going to change diffusion at change position at a faster rate. What determines this? If you put ink in a glass jar at room temperature, and also did the same experiment at a higher temperature, say boiling water, you find that that ink diffuses much more quickly at higher temperature. Okay? So these regimes of diffusion, so if you have a lot of restriction, then diffusion is going to be very, very slow. If you don't have as big a restriction, then diffusion is going to be very, very fast. So the size of the axon we have not talked about. If the axon is very large, then diffusion is going to be fast in that axon, almost close to free. If the axon is very, very small, then diffusion is going to be equally slow. So we have not talked about the concept of speed of diffusion. All we've talked about is we have diffusion in that direction, and it goes through a certain distance. So the idea behind this is this. If you plot the distance that a particle diffuses versus the time it takes it to get there, if diffusion is free, you expect it to be a straight line. As time goes on, it's going to map out larger and larger distance. Okay? But when you do this for biological structure, it starts off like almost a straight line, but then asymptotically changes to a different shape, because now diffusion is seeing boundaries. As diffusion sees boundaries, it slows down. So this change is important. This change in diffusion dynamics over time is important to give us additional information that we have not tapped into yet. Okay. In biological system, this has been done, where the diffusion, the time it takes to observe diffusion which is this time, is plotted against the diffusion measurement that you make. And again, we notice that instead of being a straight line, we see this change in behavior. Okay? So if the observation time is much smaller than the time the particle moves around, then the particle appears as if it's unrestricted. So if you observe diffusion at very short time scale, everything is free because it hasn't seen a boundary. However, if you wait long enough, it starts to see boundaries. So by looking at how diffusion changes over time, we can do the inverse. We can determine from the changes in diffusion over time to determine what is the underlying restricting structure that's giving us this temporal behavior of diffusion. This is a well-known problem. This problem, incidentally, is connected to the shape of it. It's connected to drums. Drums obey the diffusion equation. So in 1966, Kirk asked a simple question. We all know from simple physics that if I take a string and I tie it to both ends and I pluck it, right, based on the geometric properties of that string, the tension in that string, you can tell me what the frequencies of that string is going to be. However, if I beat on a drum and you hear the frequencies and you're able to determine the frequencies coming from that drum, is it possible for you to tell me what the shape of that drum is? That's the inverse problem. Okay, given the frequencies, can you tell me what the shape of the drum is? That was the question he posed back in 1966. Okay? That question was answered by two mathematicians in 1991, Caroline and David. These guys don't look like mathematicians, right? So anyway, these guys answered the question that the answer is no. You cannot tell the shape of the drum from the spectrum, the frequencies it gives you. However, you can tell the perimeter the drum has. The only time you can tell this exactly, if the drum is circular, in other words, you have a conventional circular drum, then it will be a unique answer. You can tell the shape of the drum. But if I give you a range of frequencies, I can come up with different shapes, like they show here, different shapes that give you exactly the same frequency range of drumming. So they solved this problem. But they said that from the spectrum, you can determine the perimeter of the drum. And this is what basically we're trying to do. Given the fact that diffusion changes with time, and as the changes in time are determined by the boundaries that the water molecules that are restricted are seeing, if we know how the diffusion changes in time, is it possible to inverse image, basically to get what the underlying restrictions are? This is the question we're trying to answer. And it turns out that yes, we can determine the perimeter or the perimeter of the restriction, which is important. One example of an experiment that was done back in 2008 was we looked at 5 different tubes, okay? This is the largest tube and this is the smallest tube. If you have a range of tubes where the large one is this and the small one is at the bottom, if you look at the diffusion in those tubes along the dimension where the diffusion is restricted, you find that they plot out different curves, which I apologize, the colors are not very clear here. But if you do diffusion using those gradients that I showed, all you do is you probe frequencies at what is called DC, or low frequencies over here. At low frequencies, you cannot tell the differences between these different restrictions. However, if you probe at higher frequencies, you'll be able to tell the differences because they start to spread out. In other words, the change in diffusion coefficient over time due to restriction carries with it frequency information that we can use to design gradients that we use to probe the diffusion. Okay, that's the basic idea. And when you do that, you end up with things like this. And I tie this back to the question I talked about, which is imaging historically has given us structural information. And now we're trying to tie it to disease processes at a much earlier stage at a cellular level. And this is a classic case of that experiment. So in this case, we have an axial slice through the head of a control, basically somebody who is normal, no ailments, no disease, no pathology. And then we have 2 cases of multiple sclerosis. Now, multiple sclerosis is a demyelination disease. It takes those axons that I showed you and breaks them up. Okay? It takes away, so the axons have an insulator that insulates the electrical signal that's passing through. It takes that away and throws it away. When it does that, then diffusion along that axon doesn't exist anymore in a restricted sense. That axon becomes free diffusion because there's no boundaries anymore. So in this case, when somebody came in with MS, they would do what is called a FLAIR sequence, which looks at structural information. And somebody who's got severe cases of MS or multiple sclerosis, you show in a FLAIR, you show these bright regions showing areas where that process has taken place and the axons have been destroyed. Okay, so the person has significant motor difficulties and other deficiencies. In this case, this person here doesn't have severe multiple sclerosis. So we take a pixel here that looks like it's normal. In other words, it's not bright. And we take a pixel here that is obviously a multiple sclerosis case based on the FLAIR. Okay? If we did a FLAIR on this case over here, we'll see that this person doesn't have multiple sclerosis in that area based on the fact that we don't see any brightness in that region. The trouble with that is over a period of time, that area too will become bright. It's just that we don't have the sensitivity to see it. But we know that multiple sclerosis destroys the restriction of diffusion. It destroys those axons. So if you do a diffusion experiment, we should be able to determine at a much earlier stage whether or not this region here is starting to be affected. And this is exactly what this plot shows. This plot shows that for control, you have much higher restriction of diffusion. For a lesion, like in this case where we have a lot of multiple sclerosis, you see the restriction is going away. We're going back to Gaussian, meaning it's free diffusion. However, this case over here, the third case, is normally appearing white matter. In other words, on a flare, when we look at these peaks over here, it looks like everything is good. But on a diffusion, we have much higher sensitivity showing that there is a case of multiple sclerosis in that case. So in other words, if somebody got screened with a diffusion type image, they would be able to tell that that person is starting to develop multiple sclerosis at a much, much earlier stage and do interventions like drugs that slow down this disease at a much earlier stage than is possible just using FLAIR, which basically by the time you get structural information, it's too late. That's one application. Another application that really made diffusion become very widely used in hospitals is stroke. When somebody has a stroke, you typically, the brain dies in that part because it's not getting oxygen. It starts to swell, and you get a lot of fluid in that region. If you do a normal T2 experiment, you might see some of the swelling, but swelling shows up much, much later. Whereas if you do a diffusion will right away tell you that that part of the brain doesn't have the anisotropy, basically doesn't have the directional character anymore at a much earlier stage. And you'll be able to then do something to stop the stroke from spreading. So the first line of defense in a hospital when somebody has a stroke is to do a diffusion experiment. And when they do a diffusion, they can tell right away whether or not that person has a stroke.
Is this a procedure now?
It's a procedure in almost every major hospital in the US. When you come in with stroke symptoms, right arm, that numbness and whatever, they put you in, they do a diffusion experiment, they can tell you right away, go home, or we have to operate right away. In the past, you go in those procedures. They will go in, they will do a structural imaging. They look at you and say, no, we don't see anything. And then the stroke will hit.
Between stage 2 and 3?
Stage 2.
If you don't go through this procedure. If you don't go to this test of diffusion, how long does it take from this situation where everything looks clear to the one?
I don't know. That's patient specific. That's patient specific. The point about the MS case is there are drugs that will slow down the demyelination. However, the earlier you catch it, the better. So you can be put on a drug regime. Right? So the sensitivity is very important. Similarly for stroke, stroke is much more serious because somebody comes in, they don't do a diffusion experiment, they have no idea, they don't know for sure it's a stroke, so they observe you for an hour or so and then they send you home. And then if it's a stroke time is the most important thing. So the longer you wait, the more part of the brain you lose. Diffusion will tell you for sure you have a stroke or you don't. And then they would do an intervention based on that. Okay.
So this diffusion test is by MRI machine?
Yes. Yes. Yeah. Yeah. So if you go in, if you have a stroke, and God forbid you don't have a stroke, but you go in, they do a diffusion experiment on you. They will tell you right away whether or not you have a stroke and how severe the stroke is, and then they will either give you drugs or they will take you in and try to open up the vessel intravenously. Yeah?
Can you also detect progressive degeneration as in Alzheimer's?
Yeah, so Alzheimer's, I don't know. So this will detect diseases that basically destroy structure in the brain at a cellular level. So in this case, the MS case, multiple sclerosis, is destroying the axons. Okay, any disease at a much lower cellular level that does not destroy structure like this, people are investigating specific tags to that disease, and that's a major research area. And in fact, this is one avenue of trying to get going beyond structural imaging, where we can look at processes at the cellular level. This is one avenue. There's other avenues of looking at cellular level where you target specific things that will tell you about that disease process. at a much earlier stage. So I don't believe that for Alzheimer's, you'll be able to take diffusion will tell you something significant unless somebody knows more about Alzheimer's in terms of whether changes structurally, what happens.
Does alcoholism destroy brain?
Yeah, it's a well-known fact that alcohol destroys neurons, but we have billions of them. One?
If you take a brain of an alcoholic and a normal person, can you see the brain?
So we don't see neurons here. We see axons. We see the wiring.
But does it become dead material or does it remain?
So what is destroyed is the signal-producing capability in the neurons, right, which are in the gray matter. That's what's destroyed. But the wiring itself, it's like not paying your electric bill, right? The wires will stay in the house, but the signal is not there.
Sorry, was we taking questions and
It's almost open. So actually, I like to do it this way because it's much more fresher in terms of directing how I... Okay, so one of the things I didn't talk about here is if you want higher resolution, instead of even just going to using a lot of directions, you want to go to high field strength. So the highest clinical field strength right now is 3 Tesla. Now, for comparison, the Earth magnetic field, depending on where you are, is about 0.5 Gauss, which is very, very small. So 3 Tesla is a big field, but the kind of fields I'm working on is about 21 Tesla. And that gives you a lot more resolution in terms of tracks that you can see, issues you can resolve, but it's all done with much more cooperative patients. Rats and the like. And the fourth thing I want to talk about is by looking at the temporal evolution, which I hinted on, there's another avenue of resolution we're going to be able to untap by just looking at how the diffusion changes with time and being able to use that to inverse image restrictive structures. I'd like to conclude by, of course, acknowledging the people that I work with, both graduate students and postdocs, as well as collaborators in various institutions. And also like to take this opportunity to thank NYU for asking me to come and give a talk. It's an enjoyable experience. I've never been to the Gulf, and thank you.
Thank you, Professor, for a very impressive presentation. Do you know if in Europe something similar is going on?
Europe?
Yeah.
Oh, yeah.
Where in Europe? France, UK, Germany?
All of the above. All of the above. So diffusion really had a major breakthrough when a group at Stanford grabbed a cat off the street, gave it a stroke, put it in a scanner using diffusion, and showed that you could determine that somebody is stroking, or an animal is stroking at a much, much earlier time than is possible. So everybody jumped into the field. So every single significant country that does research has a program on diffusion. And certainly Europe is one of them, one of the places where this is done.
Sure. My understanding is that the difference in size in an axon relates to its utility, its functional utility.
Yes.
So I'm just trying to put those things together, and I can't. Can you comment a little bit about the size?
So right now, we determine, based on the experiment that we're doing, we're determining the average size of the neuron, right? So what I'm trying to do, the last piece of the talk, number 4, is we're trying to be able to, instead of looking at the average, be able to distinguish these different types of axons based on their sizes. And the only way to do that is to go to a different type of imaging where we look at how the diffusion changes as a function of time, a different type of processing, which we're not doing right now.
Does that also then show neuroplasticity? That shows how the brain is changing over time? Whether healthy or weird pathology?
So plasticity, plasticity has to do with the neurons themselves, not the axons, right? And we're not, all we're doing here, well, all we're doing here is we're looking at the wiring itself. We're not looking at the engine that's producing the signals, the neurons in the gray matter. So that's, I mean, if you can find a modality that can look at the signals themselves at the neuron level and be able to identify them, give them spatial distinction as to where they're coming from, you're on your way to Stockholm. That's the last, and that's the last big holy grail of in biology, is to be able to determine neuronal signals on a localized basis and say, somebody tapped their finger, the signal came from here and then went this way. That's huge.
You say there are
many.
You say there are many.
Yeah, there are many neurons, yeah. And functional MR is a secondary way, it's a hemodynamic effect that connects somehow the electrical activity to the oxygen consumption. Okay, so serious neuroscientists don't even consider functional MR. They think it's too crude, but it's the only game in town and every psychology department is jumping in. Yeah.
Are there ways you can combine this with other methods of scanning to follow real-time the location of a signal and compare that with the axon tracks, or is that something they're also still working on?
So compare the axon signals to, I'm sorry?
Like basically, essentially to be able to follow a signal through the brain in real time. Is there anything that you can see an electrical signal or the product of electrical signal?
So the only thing that we have for looking at electrical activity in the brain is something like EEG or MEG, but that's outside, and it just shows you the assembler signals that you detect from outside. You have no spatial localization at all. So what you're trying to ask me is, can you give us conductivity? Now you know the neurons, where they start. Well, you know where the axons start and where they end. Can you give us conductivity? Again, that's a Stockholm question. Oh, there's a lot of people working on this. It's just very, very hard. The electrical signal that's associated with neuronal activity has a magnetic field associated with it. Unfortunately, that magnetic field is so small that it does not interact in any way with the magnetic field that we've applied. So there's no good way of detecting that signal. But some clever young kid is going to come up and say it's right there. It's just one of those unknowns that needs to be resolved. It doesn't have to be with MRI. The basic question is this: can you give us localized spatial? Can you give us localized electrical activity in the brain? So we know exactly where it comes from. You can come up with any technique, and that's a big question. There's a lot of people working on it. It's just hard as hell. In fact, Darwin said that understanding this, I'm paraphrasing, but he said, understanding the brain and electrical activity in the brain is the last citadel, and it will not be taken by direct storm. So people have tried the direct approach, and it hasn't worked.
One question, how has your 21 Tesla changed your fiber tracking as compared to 3 Tesla? I mean, how, just to get an idea about that you're doing work on 21 Tesla, so how does the diffusion change? I mean, just fiber tracking, resolution? Or
yeah, what? So MRI, as wonderful a technique as it is extremely insensitive. So for every 1 million water, every 1 million protons, basically hydrogen, for every million, only 3 give you a signal. Yeah. So in order to get signal, you have to go, that's why people go from 1.5 Tesla to 3 Tesla, because the higher the field, the more signal you get. By 21 Tesla, you have more signal. That's problem number 1. Problem number 2, when I introduced diffusion, I told you that diffusion works by decreasing your signal. Okay? So on top of those 3 protons that we talked about, diffusion works by even further decreasing the signal. So by going to higher field strength, you start off with a big, you have like, that's your starting point is big, and then you start eating into it to get more resolution of the issues of crossing fibers, kissing fibers, angled fibers, and so on. So SNR is your friend in this problem. The more SNR, the better.
Can I just ask, is this for the general public or private patients?
This stuff here?
Yeah, diffusion.
Oh,
for
diffusion.
early intervention, yeah.
Yeah, so...
You're saying it's worldwide already?
So I don't know a single center in the US that has an MRI system that if you went in and you had a stroke, that they would not put you in and do diffusion on you. Diffusion had such a huge impact in terms of being able to, I mean, stroke is the second leading killer, I think, in the US, in fact, in the West. So diffusion was a huge breakthrough that the rush to productize it was just phenomenal. So almost every major center does it. The only places, the places that don't do it are the ones that don't have MRI systems, because MRIs are expensive. So each Tesla is $1 million. So each Tesla. So one Tesla, so the system I was talking about was 1.5 Tesla, that's $1.5 million. The next level is 3 Tesla, that's $3 million. So don't ask me what 21 is. No, 21 is not a human system. It's not big enough to put your head in. So that reduces the cost.
The example that we just see now is application of diffusion in the brain because of the structure.
Yeah.
But also we can apply it to other organs, right?
Yes, absolutely.
Like tissue and where we can find movement.
Absolutely. You can apply to the tongue to show those fibers in the tract, in the tongue. So every part of your body's got fibers in it.
Yeah.
Right.
Okay.
And
thank you.
But the brain is more interesting because that's where a lot of pathologies are. Yeah.
Okay.
Hi, my name is Herlina. My question is this an affordable treatment for the average patient since it can be quite expensive?
Is it, I'm sorry?
An affordable treatment for the average patient.
Oh, an affordable treatment for...
If you happen
I think
to know.
if you have, I don't know about this country, but well, certainly in this country it's affordable.
In the US.
but in the US, if you have health coverage, it is purely affordable, yeah.